All right. So last time, the most important thing I told you was the definition of a face. And I mean, I told you a bunch of important things, but a face. So if P is a polytope and H is some vector in R to the D, then it defines a face of my polytope as just the set of all points in the polytope which maximize the dot product with H. And we had some properties for faces of polytopes. And so today I'm going to try to actually give you some examples and draw some pictures, hopefully. And we're going to practice this definition on different kinds of polytopes. And then we're going to try to connect different examples of polytopes together. So, and before I do that, let me introduce an important concept, especially from the combinatorial perspective. So the F vector of a polytope P is f of P, which is a sequence of numbers, f negative 1, f0, f1, all the way up to f sub d, well, f sub the dimension of polytope, where each f sub I is the number of I-dimensional, let me use k, the number of f sub k is the number of k dimensional faces of my polytope. You start with a polytope and you get a sequence of number of positive integers. And we always have f negative 1 is equal to 1, and the top part is also always equal to 1. That's the unique top dimensional face. This is the unique empty face. And f sub 0 is the number of vertices of P, and f sub dimension minus 1 is the number of facets. So these are the two most interesting numbers. Facet is a face of codimension 1. So any questions so far? Okay. Examples. And here I'm going to again be interactive and ask everybody to tell me the answer. So the first example we already briefly mentioned before, the simplex. Simplex delta d minus 1 is the convex hull of the basis vectors, the standard basis vectors in R to the D. Standard basis of R to the D. All right. So here is a question. What is the total number of faces of a simplex? And while you're thinking, let me try to draw the case d equals to 1. My simplex is a line segment, and d equals to 2. My simplex is an equilateral triangle in the 3-dimensional space. When d equals to 3, the simplex lives in 4 dimensions, but it looks like a regular tetrahedron. So what's the total number of faces? Yeah. Oh, okay. So you're saying each each next polytope is what's called the cone over the previous polytope, or the pyramid over. Yeah. Oh, okay. Any 2 to the d. That's interesting. Answer 2 to the d. Any other options? Is it 2 to the d? 1, 2, 3, and the empty face. 4. Okay, there is a 2 to the. Yeah, that's the correct answer. But how do you prove it? And I mean, you can prove it using the pyramid construction, but let's use this definition here. Let's say I take let H be a vector. How do I find this face here? Yeah. Oh, perpendicular. I see. So you wanna choose the set of vertices in advance and then find the H that sort of points onto that. Okay, but let's say I give you an H. How do you find the face then? Because then we're gonna, yeah, but let's first do the reverse construction. I mean, how do I find this sounds maybe tricky, but yeah, let's say H is H1, H2, etc. H sub d. I'm actually, you want to be more constructive? No, but let's say this is actually going to be constructed at the end. For now, let's say take any H, and then we want just analytically compute the face. How do we do that? Okay. Okay, nice, very nice. The dot product with EI is just HI. So if I want to find a vertex, remember the vertices are, if a polytope is given as a convex hull of these points, then the vertices are the ones that maximize a dot product with a given H. So in particular, well, in general, if you have several H's, several coordinates which are maximal, then the face is going to be the convex hull of the corresponding vertices. So H, the convex hull, I, where HI is the maximum. Okay, yeah, that's correct description. And now you can see that it's very much constructive. If you give me any set of vertices, I can just easily find a vector which has these maximal coordinates. I don't have to find anything perpendicular. I mean, it's going to be perpendicular automatically to the corresponding face. All right, yeah, very nice. So, and what is the F vector? I should write down the F vectors. What is the F vector of the line segment? Say it louder. Yeah. 1, 2, 1. F delta 1 is 1, 2, 1. Nice. Empty face, the vertices, and the one-dimensional. And here, what is the F vector? Oh, nice. 1, 3, 3, 1. These look like combinatorial numbers. 1, 4, 6, 4. Nice. So in general, it is correct that the I coordinate of the F vector is just D choose I. Okay, this was easy. Let me try another one. The next example is the Hypercube, which looks like another easy polytope, but then later we're going to see some non-trivial things are going to happen for the Hypercube. So the hypercube is usually it's convenient to either take 0, 1 to the d or -1, 1 to the d. Let me take the latter one for this example. So it's just a set of all points which are between -1. So each coordinate is between -1 and 1 for each I. And the typical example, which we all know, this. Okay, so what is the number of vertices? Yeah, 2 to the d. Okay. What is the number of, let's say, facets? Two d. Okay. What's the number of edges? Euler's formula. Oh, you want to apply? Okay, so for three-dimensional hypercube, that Euler formula works. Actually, there's an Euler formula for arbitrary polytopes, but we're not going to discuss it yet. So yeah, the number of edges looks kind of tricky, right? So it's actually easier to compute the number of k-dimensional faces just for arbitrary k. And so how do you find a face? Let's say you take a vector h. How do you find Oh, okay, nice. And what about the 0 h's? Doesn't matter. Okay. So if h is 1 to hg, then f sub h is the set of points of the form x in r to the d, where xi is equal to 1 if hi is 1, I is -1 if, well, if hi is positive, if hi is negative, and xi is arbitrary if hi is 0. By just taking the dot product, you see that the maximum is going to be here. So in particular, what is the dimension of such a face? It's the number of zeros in H. Very cool. So what is the k -1 to the 1 to the d? What is the number of k-dimensional faces? Times d choose k. Oh, okay, that is correct. All right. And what is the total number of all faces of all dimensions? Say again? D times 2 to the d. That's actually d plus 1. Oh, wait. So what about, let's say I draw d equals to 1, it's line segment, d equals to 2, it's square. So here the number of faces is 4. Here it's 10. And what about here? Okay. Oh, that's a good point. Yeah, there's the single cube that's inside, which corresponds to the interior, and you have the empty face. Okay. So how many? 28. Okay, Rubik's cube. Nice. So 4, 10, 28. What's the answer? What's the pattern? 3 to the d plus 1. Nice. Why is it 3 to the d plus 1? Binomial theorem. Indeed, this is, well, the empty face is not, when d is -1, this, sorry, when k is -1, this is, yes, a bit weird. But anyways, if you just take 1 plus the sum over k from 0 to d, 2 to the d minus k, as d choose k, then you get 3 to the d by the binomial theorem. And what's the direct way to see that the number of faces is the power of 3 without applying the binomial theorem? High-dimensional Rubik's cube. Okay. So can you say what is?
Well, have this dimension. Actually, coordinate that little.
Okay, yeah, very nice. Yeah, that's actually, so what you're saying is basically for each I, we have 3 options. So 3 to the d. Right. So in a sense, yeah, I mean, that's very nice. So in a sense, this, if you just count the faces of the hypercube, you get some already mildly non-trivial combinatorial identity. That's all right. Now let me escalate into one more example. So the next example is going to be the hypersimplex, which is kind of like a mix of a cube and the simplex. So it depends on it's, by the way, one of my favorite polytopes, maybe like top 2 favorite. And so you fix 2 integers, 1 less than or equal to k less than or equal to d minus 1. And then you define the hypersimplex delta k comma d is just by definition going to be a slice of the hypercube. I'm going to take the hypercube between 0, 1 to the d, and then I'm going to just ask that the sum of all coordinates d is equal to k. So I take a slice of the cube where the sum of coordinates is k. So what's the dimension of this polytope, let's say? Seems like, yeah, it should be d minus 1. Okay, yeah, let me try to draw a few examples. Maybe delta, what is delta 1 to? Diagonal of a square. Okay, yeah, so it's just a line segment which is contained inside the, if you have a cube, then it's the diagonal of the cube. Okay, which is, this is 0, 1. All right, now let me try delta 1, comma 3. Yeah, it's a triangle in a cube. Okay, so let me actually try to draw a bigger cube. It's h. So if this is the origin, then I take these 3 points. I take the convex hull. This thing is delta 1, 3. What about delta 2, 3? Delta 2, 3 is what? Same thing, but flipped. Yeah, okay, so here like this, which in this picture is the convex hull of these 3 points. And can we try delta 1, 4? Yeah? Okay, delta, nice. Delta 1, d is just by definition the d-1 dimensional simplex. In this case, it's going to be what? Tetrahedron. Okay, and I guess what about delta 2, 4? Seems like an octahedron. Question mark. Maybe try to draw an octahedron. Seems like an octahedron. What about delta 3, 4? Okay, it's an upside. Okay, let me just draw the tetrahedron again. I can't really draw the upside down one. All right, so and that's all correct, as we're going to see in a little bit. So what is the number of vertices of delta k, d? D choose k. Okay. And why is that? If I give you an h, d dimensions, yes. Okay, so right, you're saying that I should maximize my basically, if I want to maximize the dot product of this guy over this set here, I should choose the k maximal coordinates of this vector, and then take the corresponding xi's to be equal to 1. That's intuitively, that's f sub h is basically, okay, how do I write down f sub h correctly? Let me write it down like this. It's the convex hull of E sub I, where I is a subset of the set of I where hi is maximal, and the size of I is equal to k. And what do I mean by E sub I is E sub I is just by definition the sum over I in I of the standard base vectors. All right, so I get n d choose k vertices for each hypersimplex. And I can label them by k element sets. So this is E1, E2, E3, and this one is E12, E23, and E13. And the red guy is, yeah, it's the same thing, E3. And then the blue guy is, what is this vertex? E13. They are, yeah, and this one is E12, this is E23. All right. So, and you can figure out the whole F vector. I'm not going to do this today. So, nice exercise to find the F vector of the arbitrary hypersimplex. But and by the way, I guess you still have to prove this rigorously, that the dot product is actually maximized at this set. I haven't actually explained this particularly rigorously, but you can do that. And oh, by the way, let me continue labeling the faces. E1, E2, E3, E4, and then this is going to be 3, E2, 4, E1, 2, 3, E3, 4, E1, 4. And so let me ask. This describes arbitrary faces of the hypersimplex. So what is the equation for, let's say, this face here? In terms of the, let's say, the x coordinates, what are the, and describes this? Okay, this equation is true, but there should be one more, right? Because it's a face. Okay, right. For all of these vertices, E12, E23, and E13, the fourth coordinate is 0. And therefore, for the convex hull, because it's a face, it's enough to just take one equation. All right, what about this face here? E2, again, x2 equals to 1. All right, that's correct. Thank you. Right, because again, for each of the vertices, this is true. So you can kind of write down what about this edge here? Okay, x4 here, x4 equals 0. It's an intersection. X equals. Okay, so but notice that actually the faces of the octahedron can be colored in 2 colors. Each face is either xi is 0 or xi is 1. And indeed, yeah, you can color it in red and blue in the bipartite way. So, but so let me mention one more observation, which is sort of weird observation. It appears that each hypersimplex is a slice of the hypercube. But it also appears that the pieces in between the slices, if I look at I have these slices, and then I look at the pieces between the slices. Looks like the hypercube of dimension d minus 1 is somehow a union of delta 1 comma d, maybe not disjoint, but sort of almost disjoint, delta 2 comma d, delta d minus 1 comma d. I don't know if you can see that, but let me try to draw this in the. So this, let me draw the square again. Here's the square. Here's the diagonal, which is delta 1 comma 2 by the hypercube 0, 1 squared. And then somehow it's a union of two triangles. A red triangle and a blue triangle. And we know that a triangle and an upside down triangle are delta 1, 3 and delta 2, 3. Well, I mean, those are equilateral triangles, and these are not equilaterals. But it's still combinatorially, it looks like delta 2, comma 3, delta prime 2, comma 3. And this looks like delta prime 1, comma 3, where prime means I don't yet know what it means. And similarly, if you look at these slices here, this is a tetrahedron. And this is an octahedron. This is an upside down tetrahedron. So this is delta prime 1, comma 4. This is delta prime 2, comma 4. Delta prime 3, comma 4. Is that a coincidence, or what is the explanation? Well, let me, yeah, what's the explanation? All right. Okay, so you're saying, okay, you're saying I can define each delta prime as just delta prime k comma d as just the subset of points of the d minus 1 dimensional hypercube, where the sum of coordinates is not quite fixed, but what should be the condition on the sum of coordinates? Say it louder. Okay, y k plus actually greater or equal to k and less than or equal to k plus 1. Let's check. For delta 1d, the sum of coordinates is between 0 and 1. It would be k minus 1 and k. All right, that's nice. Yeah, that's correct. Because each delta prime is just a slice between these two, the slice of a cube between these two planes. Now, how do I relate? How to relate delta kd to delta prime k comma d? Yeah. Oh, okay. By the way, this should be d minus 1. Yeah, that's actually a good idea. So you're saying inside the hypersimplex, I have one extra variable, which we know is between 0 and 1. So if we just project, let's say let pi be a projection from r to the d to r to the d minus 1 and x1, etc., xd to 1, etc., xd minus 1. then pretty clear that it takes this delta kd sort of isomorphically to this delta prime kd. And what do I mean by isomorphically? Because this is a right triangle and this is an equilateral triangle. So I have to define in what sense is it an isomorphism. But maybe somebody can tell me what sense is, so then pi of delta kd equals to delta prime kd. And how would you define that pi is an isomorphism? Okay.
Okay.
Okay. Yeah, that's nice. So you're saying it's an affine map. It's a bijective affine map, which it's a definition. And pi is an what we call an affine isomorphism from delta kd to delta prime kd. So affine isomorphism means affine bijection, which in other words, some determinant has to be non-zero. All right. And because it's an affine map, it rescales distances in different dimensions by some different numbers. So in particular, it's not an isometry. Well, it does not preserve distances. So how do I see this in the picture? There should be some projection which sends these two triangles to these two triangles. Or is it? Oh, okay, nice. So you just take this cube and you push it down like this, and then the red triangle goes here, and then the blue triangle goes here. And you can project it onto any face and picture. And similarly, this picture itself is a projection of some four-dimensional. There's some four-dimensional cube which has these tetrahedron, octahedron, and upside-down tetrahedron as its sections, and they project onto these three pieces. Pretty cool. And we're going to actually come back to this later, because you can try to compute the volume of the cube. That's pretty easy. 1 or whatever, 2 to the d. And then you can, well, actually, yeah, that's a pretty cool exercise. What's the volume of a simplex? How do I compute a, yeah, I should do this. Okay, yeah, in school geometry, yeah, there is a way to compute the simplex, and I can tell you the answer, which yeah, there's going to be a spoiler of what we're going to discuss later. We're going to come back to this when we discuss triangulations, but basically, if the volume, if you divide the volume of the cube 0, 1 to the d by the volume of this delta prime 1 comma d, which is the simplex. It's this simplex right here, not the equilateral triangle, but the simplex here. Then you get a number, and that number turns out to be. Can somebody guess actually? Cool. Like here, a square is a union of two triangles, so the answer should be 2. D minus 1. Can I actually draw the picture? So you're saying here it should be 2. D minus 1 is 2 here. But there is already one, there is 2 simplexes here, and there is a bunch more in the interior. Something factorial. What factorial? D factorial. Okay, yes, thank you. That is a correct guess. And we're gonna, yeah, so there is a triangulation of a cube, which uses exactly d factorial simplices. Not too hard to see which constructed explicitly, but somehow this d factorial is the sum of, because the cube is a disjoint union of these delta primes. Take the volume of delta 1, delta prime 1 comma d, plus the volume of delta prime 2 comma d, plus etc., plus the volume of delta prime d minus 1 comma d. And then you divide each by the volume of delta, each by the volume of delta prime of the simplex. So you get a bunch of numbers, and they're all going to be integers, and then they sum up to d factorial. So the question, which I'm not going to answer today, you can try to think about it. What is each of these numbers? What are these integers that sum up to d factorial? Like for instance, the volume of the octahedron is what happens in general. Yeah, that's the question. And oh, by the way, I should mention, because I think I forgot in the first lecture, I should have told you why you should study polytopes. So maybe I should, and I mean, not only polytopes, but matroids and things like that. And I was actually, so yesterday I was watching a biology lecture I decided to learn genetics. And there was this, the professor was telling about, this is actually a true story. The professor was telling that there is 2 types of leukemia. And somehow these patients require very different treatment of different types of leukemia. So how can you tell them apart? And how do you even know there is 2 types of leukemia? And then he says that the actual method is you take these cells and you measure the percentages of different genes in these cells. And there is 21,000 genes, so you get, and then he just says that like each patient corresponds to a point in the 21,000 dimensional space. And I was like, okay, this is interesting. And so the actual method is you plot these patients as points in the very high dimensional space, and then you somehow just separate them by hyperplane. You write a computer program which deals with these very high dimensional configurations of points and chooses the treatment plan for leukemia based on that. So yeah, and of course, I mean, looking at the roster of this class, I know that many of you probably don't plan to be mathematicians. So you may be wondering, like, why are you taking this class? And the answer, I guess, is it's nice to have geometric intuition for high dimensional point configurations. If you want to do some image recognition, then each image is, each pixel gives you a coordinate. So it's, again, a high dimensional point. So if you want to distinguish between different images, they're going to give you different points. So anyways, it's nice to have some familiarity and intuition. And especially with the matroids, it's much easier to put them into computer. These vectors may have very close coordinates, so you have to, anyways, there's all kinds of computational stuff which I'm not going to discuss, but at least it's nice to kind of learn to love polytopes and high dimensional vector configurations. So any questions so far? Okay, no questions? Now I'm gonna talk about, I guess, my favorite polytope. This is the top one, the Permutahedron. What is the Permutahedron? Well, first of all, it has to do with permutations. A permutation, in case you forgot, permutation is a bijection from bracket n to bracket n. Just take n numbers and permute them in some way. And let me denote this bijection by W. And I have this Sn is going to be the group of such bijections under composition. And then the Permutahedron phi sub n is by definition the set of all. What you do is you take the convex hull of set of points, W of 1, W of 2, etc., W of n, where W is a permutation. So you take n factorial different points in the n-dimensional space. And these points are just you take vector 1, 2, all the way up to n, and then you permute the coordinates in some way. So you get, and then you take the convex hull, so you get the Permutahedron. What is the dimension of the Permutahedron? N minus 1. Okay, and why is that? Nice. Okay. Right. So the dimension is n minus 1 because, well, it's at most n minus 1 because phi sub n lies in the plane the sum of where the sum of coordinates is equal to n choose 2. All right. So maybe I should try to draw some examples. Almost out of time, but so what is E2 or pi 2? It's a line. Yeah, it looks like this. So if I draw it in coordinates, then this point is 2, 1. This is 1, 2. These are the two permutations, so you get a line segment like this. All right, what is pi 3? Octahedron. No, hold on, it should have dimension 2. Well, it's actually, if you try to draw an octahedron like this, without the extra stuff in between, yeah, it's a hexagon. Why is it a hexagon? Whoops. Yeah, anyways, I guess we should just stop here and next time discuss why it's hexagon, what's the number of vertices, and what are some other properties. So that's it. Thanks for coming, and see you on Friday.